All right. And that gave me 0 and 4 on my number line. And then I did my interval testing like we do. And I got a plus minus plus, which means it was increasing from negative infinity to 0, and then from 4 to infinity, and then 0 to 4 it was decreasing. Max or mins happen wherever it changes. It changed at 0. It was going up and then down. So that's a max. That's why I have a 0 there. And then at 4 from negative to positive, which means that was a min. And to get these y values, I plugged back into the original. So this is a big number, negative 256. So we plugged 4 in. 4 to the 5th is a big number. 4 to the 4th is a big. So you ended up with being negative 256 for that problem. So the relative min was 4 negative 256. And the max was 0, 0. Right? So hopefully by now we're starting to get a little better at all the increasing and decreasing stuff. Right, any questions on the first derivative? All right, so then second page here, we have the second derivative. All right, so the second derivative is right here. I know it's kind of messy there, but it says 20x cubed minus 60x squared. So then we find the critical values by setting equals 0, solving. Took out a 20x squared, and then it's x minus 3. So we get 0 and 3. When we did interval testing here, you would have got a negative, negative, positive. So it's concave up from 3 to infinity, concave down from negative infinity to 3. And then the points of inflection happen. There is no point of inflection at 0 because it's negative, negative. It only one at 3 because it goes from negative to positive. And then, so that's where we have 3. We plug back into the original to get my y, and another big number there, negative 162. Yeah, you can have that. All right. So that's the second derivative. Oops. So then we can take all of the information from the two number lines, and that's what you're going to put on this big number line. You put any critical values that were listed. So we had 0 and 4 on the first one, 0 and 3 here. So we have 0, 3, and 4. Up top, we write where it's increasing and decreasing. So it was increasing less than 0, that's why I have it here, and greater than 4, that's why this is here. And then decreasing between 0 and 4. All right? And this is going to tell us what our curves look like. Then we do the same thing for concavity. It was down less than 3, and it was up greater than 3. So this will tell us what our curves look like, right? Increasing and down, decreasing and down, decreasing and up, increasing and up. Then we go to our graph, and this is what our graph will end up looking like. But how we got there was we first had to plot all our points. There's no asymptotes in a polynomial. We would graph it, we would do the asymptotes now as well, but there is none. We graph the x-intercepts, which we had here at 0, 0, and at 5, 0. We had a relative min at 4, negative 256, and a point of inflection at 3, negative 162. Those were our only points. Notice, see how I just labeled it, negative 256, negative 162, roughly somewhere between. Obviously, we're not going to put a whole bunch of slash marks for that. And then we just play dot to dot, right? Making sure the curve matches what it says in this number line above. So increasing and down, that looks like that. Then it goes decreasing and down. Point of inflection, it changes to decreasing and up. And then it goes from increasing and up. Not the best line, but you guys get the idea. All right. And then you could always go back and check, does it make sense that this was a max? Yes, we had a 0, 0 was a max. Point of inflection was here. All right, we had a relative min was this point, 4, negative 256. So you can always go back and check to make sure that it all makes sense. All right. All right, questions? Okay. All right, so we're going to work on this problem right now today. All right, I'm going to do this, show you guys how to do this with the fraction. And then I'm going to assign the one that comes after it, B, that you'll do for homework over the weekend. And this is all from the same worksheet that you guys did the first night with the limits. All right. All right. So all of this, same sort of idea. It's just it's a little different because we have a fraction. A few other things we just have to be concerned with. Number one is we will have asymptotes. All right. So you have to remember, how do I find a vertical asymptote? Well, you find a vertical asymptote by setting the bottom of the original. Remember, all 6 of these things up here have to do with the original. Don't worry about the derivative. first derivative until you get to increasing, decreasing. You worry about the second derivative with concavity. All of 60s, the asymptotes, the x and y intercepts, and symmetry have to do with the original. So we set the bottom equal to 0, and it's 2. So you write x equals 2. That's it. There's your vertical asymptote. Now, to do the horizontal and the slant, all right, you have to look at the degree at the top and the degree on the bottom. We follow our rules. If the degree was larger on the bottom, we would have 0 as our horizontal asymptote. That's not the case. If it was the same, we would take the leading coefficients. Not the case. It's the case where you have it bigger on the top, which means there is no horizontal asymptote. This is a slant asymptote. To find a slant asymptote, you must divide. All right, you're going to divide. The easiest way, especially since this is a linear term, which pretty much the ones I give you will be linear, is to do synthetic division. Synthetic division is done by whatever makes this equal to 0 goes in a box. So that's 2. You then put the coefficients of each term. So the coefficient of this term, 1. Coefficient of that term, -2. The constant, 4. I am not going to care what my remainder is. The remainder is not important. This number here is your constant. This number here is your coefficient of x. If there was another number here, that'd be your coefficient of x squared. So I bring this down. That's 1. I then multiply these two numbers. 1 times 2, that goes here. You add these numbers, and that's 0. Right? I'll keep going, but 0 times 2 is 0, and then this would be a 4. But like I said, I don't care about the remainder. So this is telling me the equation of my slant asymptote. So it's going to be y equals, this first number is your coefficient of x. So 1x, which is just x, plus 0, I don't need to write that. If that was a 2, it would be y equals x plus 2. If it was a -2, it would be y minus 2. It's a 0, so it's just y equals x. All right, so my slant asymptote, that's the equation of the line. That's going to be our slant asymptote. Any questions on that? All right, this is the one that's the biggest pain when we have a slant. All right, but I'm not going to make it so it's going to be difficult. It will be a line. It's not going to be some parabola that we're going to have to graph as the slant asymptote. It will just be a line, y equals x plus 2, y equals 2x plus 1, something relatively simple. Okay. All right, so then for x-intercept, we set the top equal to 0. So normally just set the whole thing equal to 0, but I said, remember, with a fraction, it's the top equal to 0. Now, you cannot factor x squared minus 2x plus 4. That does not factor. So you would have to do like completing the square, quadratic formula. All right, here's a little hint. If it can't factor the top and you have a quadratic like this, that means it has imaginary zeros. I'm not going to give you one that's going to be zeros of like 3 plus or minus √5. It's not going to happen. So in this case, if you were to go and solve this, you would get imaginary answers, which means there is no x-intercept. It is possible to not have an x-intercept. Okay. So once again, if you can't factor the top of a quadratic, just assume that the answers are imaginary and just put none. Now for y-intercept, you put 0 in for all of the x's and then simplify. So if I put a 0 in here, it's 0, 0, I'm left with 4, and then a -2 on the bottom. 4 over -2 is -2. So my y-intercept is 0, comma, -2. Okay. Symmetry. All right. Remember, symmetry, we put in -x. So if I put in -x and I square it, -2 times -2 plus 4, I can tell by looking at this, it's going to be neither, because I can look at the bottom and I'm going to get -x minus 2. And right away, I see one of them changed, one of them didn't. And then here, I noticed that, what was that, plus 2x? Yeah. First one changed. First one didn't change. The second one did change. The last one did. They all, top would have to change, or they all wouldn't have to change. You know what I mean? Like once you get, if you have like several terms in and one changes, one doesn't, you know right away that it has no sort of symmetry. So it is neither. All right. And if you went back and looked at our polynomial that we did previous, you could look at the graph and tell that there was no symmetry there. So it's always something that you can always look at back at the end to check your work. Does that look like it's symmetric? No. Well, then neither is probably your bet. And it will be very obvious when it's even or odd. And we'll get to those next week. We'll do some examples that actually have some symmetry to them. Okay. So then now, once you get through that, so like that's kind of like a little newer, different. We haven't done that in a while. Now we get to the old standby. We feel like we've been doing this forever of increasing and decreasing and all this stuff right here. All right. The nice thing is with the fractions, I give you the derivatives. So to find your critical values, you just have to set the top and the bottom equal to 0. So up top, I get x times x minus 4, which gives me 0 and 4. And the bottom, I get 2. But we have to remember when we're doing this, especially in a fraction, and we see it right here, the vertical asymptote of the original is x equals 2. So when I go on my number line to put 0, 2, and 4, it is an asymptote at 2. Draw it in there so you don't make any silly mistakes with making points on that, or like forgetting to put a union if you split up increasing and decreasing. Remember that the original has an asymptote there, so that will affect our answers. All right, so now we go do our interval testing. Anything less than 0. Now this is where, remember, we're plugging into the original, and use the fact that this whole bottom is squared, which means this will always be a positive. So you only have to worry about plugging into the top. All right. So if I put a negative number here, that gives me a negative there, a negative there, a negative times a negative is a positive. If I put 1, that's a positive here. 1 minus 4 is a negative. Positive times a negative, negative. If I put a 3, same thing happens. I get a positive here. 3 minus 4 is a negative 1. Still have a negative. This is positive. So I'm increasing from negative infinity to 0, union 4, even though it looks like a y, that's a 4. 4 to infinity, and it's decreasing. Now, this is where the asymptote comes into play. If the asymptote wasn't there, that'd be 0 to 4 would be my interval. But because it's there, I have to split it up to 0 to 2, union 2 to 4. Okay. Check to see where it changes. It changes at 0, and 0 is not an asymptote. So we can have a relative max there because it goes from positive to negative. And I already know when I plugged in 0 to the original, I got negative 2. That's the y-intercept. So 0, negative 2. Not only is the y-intercept, it's going to be a relative max point for us. Relative min happens at 4. Whoops. It's going down, then up. So that is a min. When I go back to the original and plug in 4, right? Remember, go back to the original up here. So 4 squared, 16. 16 minus 8 is 8. 8 plus 4 is 12. 4 minus 2 is 2. 12 divided by 2 is 6. So I get 4 comma 6 as a relative min. All right, like I said, all the same stuff. And hopefully the more you're actually practicing this, if you are doing it, the better you'll get. The key is you actually have to do it. All right, and second derivative always seems to be a little bit easier, especially if a case like this. We only have one critical value. Love when there's only one critical value. And it happens to be 2. Don't forget that is an asymptote. When you plug in something less than 2, like 0, negative 2 cubed is still a negative. So that's a negative. The top's always positive. Anything bigger than 2 gives me a positive. So I'm concave up from 2 to infinity and concave down from negative infinity to 2. Point of inflection should happen at 2, but it's a vertical asymptote. So there is no point of inflection. There's no point in this function where it will change from concave up to concave down. All right. Any questions on that middle part? Okay. All right. So now we get to the fun part where we get to actually graph this. All right. And we first have to, on the number line, so here we have these critical values, 0, 2, and 4, and 2. Those are the numbers that have to be included on the big number line. If something comes twice, it doesn't make a difference. Just have to include it once. So 0, 2, and 4. And then we figure out what our curves are going to look like. That's why we do this. We figure out what the shape, if increasing, decreasing, and the concavity of them, put it all together, makes it a lot easier. So it was increasing there, decreasing between 0 and 4, and it was increasing larger than 4, right? And all that information comes from right here. Now for concavity, the bottom of the number line, I do this. Bigger than 2 was concave up, then it's concave down there. Right? So this tells us our curves. The good thing is all these first examples all have all the curves involved. It's not always going to be the case. but good practice. Increasing down, decreasing down. What's decreasing up? Decreasing up is that. Increasing up is that part right there. All right, so now to graph this is going to be a little bit different because we have asymptotes. All right, so we got to be a little more careful with this. So the first thing we graph is asymptotes, max, mins, intercepts, y-intercepts, all that kind of stuff, points of inflection. So we had a vertical asymptote at 2. We had a slant asymptote at y equals x, if you remember. That means the y-intercept, where the line crosses, is at 0 and has a slope of 1, which means it goes up and over 1. So it's going to intercept here, the other vertical asymptote. So it doesn't have to be the most precise, but you do have to be careful because we will be graphing the other points, and you want to make sure that the point is in the right little quadrant. Meaning, if you remember anything from what graphs look like, if you have a vertical asymptote and a slant asymptote, two things can happen. If I have a curve here, that means a curve appears there. Right? There's always one on the right side of the asymptote, left side of the vertical asymptote. If I have it here, then the graph is over here. It's always like vertical angles, if you think of geometry across from each other. Right? So having that knowledge helps when we do our graph here. So we graph our points. What were our points? Oh, there was no x-intercept, so we're good there. Our y-intercept was at 0, -2. All right, so you see I have this point in this little quadrant that's down here, meaning I should have my other point should be over here, or at least that's where my curve should be. And the only other point, I can see it up here, was 4,6. All right, that was a relative min, I believe. And you can see this is 2, 2. So this would be 4, 4. 4, 6 is going to be up here somewhere. It has to be, and it is. If you went and graphed everything exact, it would be up there. All right. Should it be probably more closer to here? It doesn't have to be drawn completely to scale. I'm not worried about it. Right. So I basically right now could probably withdraw this little like picture I have on the left here, but look how it makes sense. The fact that less than 0, increasing it down, which looks like this. So there's increasing it down, and then decreasing it down is just there. And you can tell that point 0, -2. Not only was that a y-intercept, that was also a relative max. And you can see that it's a relative max. All right, decreasing and up looks like that, put a little arrow on it, and then increasing it up looks like this. And you can see this point here was 4,6. That was a relative min, and you can see the relative mins right there. All right, no x-intercepts makes sense. All right, and there is our graph. If we had a point over here, like if there was an x-intercept, say at 4, then you can expect your point, another point somewhere over there. All right, so we've seen graphs like this before, but we were able to figure all this out by just using all the derivative, first and second derivative, increasing and decreasing. All right, questions? Okay, so what I have assigned for you, and I believe it should already be up on the classroom, is you guys are going to go through and do the one that's underneath this. So I think I reattached the worksheet again. So if you already had printed it out, like great, you have it from the first night of homework. But I called it like do section 2, 1B. The reason I said that is because you can see right here, section 2, summary of curve sketching. That's where I got section 2 from, to capitalize Roman numeral 2. And then number 1, we just did A. You guys are doing B. So in the assignment, it says do section 2, number 1B. All right. And you can see you have fractions, all the vertical asymptote stuff, the derivatives, and then you go through and just kind of work. The nice thing about this one, so just looking at this real quick, the degrees are the same here. There will be no slant asymptote. There will be a horizontal asymptote, right? Because the degrees are the same. I'll let you figure out what that should be, but there will be no slant asymptote for this one, which is nice. So the picture will be a little different. See if you can get it, but hopefully you guys can figure it out. All right, anybody have any questions?
Can you post the notes from yesterday?
Yeah, so here's the issue, and I emailed another student about this. So, like, when I'm at school, that software allows me to save everything I write and post it and save it as a file, and that's what I do. When I'm at home, I don't have that same software. I'm just doing it on my computer. But what I do have is I recorded the lesson and I like upload, like I make a YouTube link for it. So I could, if I want, I can post the link of the lesson so you can always go back. And it's not an ed puzzle, so you can just like cut like I can put I'll put both of the last two lessons on the classroom. And it'll just be a YouTube link. Okay. All right. Hope I didn't take too much of your time up, Laura, today. So I appreciate it.
It's a little rude you're giving us homework on the children. I don't know.
You have until Monday. It's like one assignment. Like not half of you won't do it anyway. So you know, like, so what are you gonna do?
I don't know. A little rough.
Yeah, I know. Rough day. All right. Well, I do hope you guys enjoy the rest of your weekend. Enjoy your weekend, and then hopefully I'll see you guys Monday. Some of you in school, and then hopefully, you know, in a week after that, I get to see most of you most of the days in school, which would be good. All right. So stay safe, and if you guys are driving, please be careful. It is icy out there a little bit, so please be safe. All right, and I'll talk to you guys Monday.
Bye.
Bye.
See you guys.
Thank you.
You have a nice weekend.
You too.